Welcome to the AI Deep Dive.
Hey, it's really good to be here.
So we are doing something a little different today. Usually, we look at a specific new tool or maybe a piece of news.
Right.
But today we're tackling a document that I honestly think is going to serve as the blueprint for the next few years of artificial intelligence. It's a comprehensive survey paper titled Agentic Reasoning for Large Language Models.
Yeah, and comprehensive is, it's doing a lot of heavy lifting there. This is not a light read.
No, it is incredibly dense. And the authorship is just staggering. For those of you listening, we're talking about a massive collaboration. It's researchers from the University of Illinois, Urbana-Champaign, Meta, Amazon.
Google, DeepMind, UCSD, Yale.
Exactly. It feels like the Avengers of AI research just all got together to agree on one specific thing.
Which is that we are essentially doing AI wrong.
Or at least that we're ready to move to the next phase. Because the central argument of this paper is that we are shifting from the era of the chatbot to the era of the agent.
The agent.
And the mission of this deep dive today is to figure out what that actually means for you. Because to the average person, ChatGPT already feels like an agent, right?
It does.
It answers questions, it writes code. But this paper argues that traditional large language models, or LLMs, are just passive sequence predictors.
Passive sequence predictors.
Which sounds a bit dismissive, honestly.
It sounds a little harsh, but mechanically, it is highly accurate. If you think about how a standard LLM works, it functions like a superpowered autocomplete.
Right.
You give it static input, a prompt, and it just predicts the next most likely word based on statistics, and then the next word and the next.
It's just math.
Exactly. It produces a static output. It doesn't live in the world. It doesn't have a sense of time passing. And crucially, it doesn't actually know if its answer is true or just statistically probable.
So it's not thinking in the way we humans understand thinking. It's just completing a pattern.
Precisely.
Yeah.
It is reacting. The new paradigm what this massive paper defines as agentic reasoning.
Yeah.
It's about moving from reaction to action.
From talking to doing.
Yes. It's the shift from LLMs that just talk to LLMs that act, plan, and collaborate.
And the paper introduces this concept right away called the think-act loop. That really seems to be the heartbeat of this entire new technology.
That is the core distinction. In the old model, reasoning was basically just a side effect of generating text. But in this agentic model, reasoning becomes the organizing principle. It's the central brain that directs perception, planning, decision-making, and verification. It's not just generating words. It's generating actions to achieve a specific goal.
Okay, let's slow down and unpack that a little bit, because reasoning is a fuzzy word. But the paper gets very specific about the mechanics of this. They define agentic reasoning essentially as the ability to navigate a problem space.
Right.
And they use this theoretical framework called the POMDP.
The partial observable Markov decision process.
Yeah, that is a massive mouthful. I feel like we really need to translate that into plain English before we move forward. Why does an AI need a POMDP?
It's actually a very intuitive concept once you strip away the math. Imagine you are playing a video game, maybe a strategy game or a dungeon crawler.
Okay, I'm with you.
But the map is covered in that fog of war. You can only see the room you are currently standing in. You can't see the exit, and you definitely can't see the enemies waiting in the next room.
Okay, so I have partial observability. I don't have the full picture of the game board.
Exactly. Now, standard LLMs are trained on the whole internet, so they sort of act like they have the whole map. They act like they know everything.
Right, they're very confident.
Very confident. But an agent actually acting in the real world, say an agent trying to book a flight for you, it's operating in the fog.
Yeah.
It doesn't know if the flight is sold out until it checks.
It doesn't know the price until it looks at the website.
Right. So because it is in the fog, it needs a way to remember where it has been and guess where it is going.
Okay.
In the POMDP model, the agent has to maintain an internal state. Think of it as a mental scratch pad or a memory log.
Like an inner monologue.
Yes. It says, internally, I already checked Delta, and that was too expensive, so now I'm going to check United. That log, that inner monologue, is what the paper calls the reasoning trace.
And this connects to another core concept. They discuss the latent space.
The latent space is where the thinking actually happens. The paper argues that for an agent to be truly intelligent, it can't just immediately react to what it sees.
Right.
It needs to process information in this hidden internal space before it acts. It heavily mirrors the difference between System 1 and System 2 thinking in humans.
That's the Daniel Kahneman concept, right?
Exactly.
Where System 1 is fast and instinctual, and System 2 is slow and deliberate.
Right. If I ask you what is 2 plus 2, that is system 1, you don't calculate it. The answer just appears in your head.
Yeah.
Current chatbots are very system 1.
Yeah.
You ask a question, they blurt out the first statistically likely answer.
They don't pause?
They don't. Agentic reasoning is all about forcing the AI into system 2. It's about creating an artificial pause where the AI says, wait, let me think about this. Let me break it down. Let me verify my assumptions.
So we are essentially artificially inducing a pause and think moment in the software.
That is the entire goal.
Yeah.
And the paper outlines 2 main ways, or optimization modes as they call them, to build this capability into an AI.
Right. They call these in-context reasoning and post-training reasoning. And reading this, it felt to me like the difference between giving a new employee a really detailed checklist versus sending them back to grad school.
That is a fantastic analogy, actually. Let's look at in-context reasoning first. This is essentially software engineering for AI.
Okay.
You aren't changing the AI's actual brain. You aren't touching the underlying model weights. Instead, you are changing the workflow around it.
So you're giving it the checklist.
Yes, you are giving it a scratch pad, giving it specific instructions on how to break down a problem, or designing a prompt that forces it to show its steps.
So when I see people online using prompts like think step by step or take a deep breath and work this out, that is a primitive form of in-context agentic reasoning.
It is. It absolutely is. But it gets much more complex with something called orchestration.
Orchestration?
Yeah, where you program a rigid structure for the AI to follow. You code it to say first do A, then check B, then if C happens, do D. You're imposing a reasoning structure from the outside.
Got it. And then post-training reasoning is the grad school approach.
Correct. This is where you actually dive in and change the model's parameters, its weights. You use reinforcement learning or fine-tuning to fundamentally alter how the model thinks at its core.
You're rewiring the brain.
You are. You are training it to internalize that reasoning process so it does it naturally without needing a complex prompt to tell it to take a deep breath.
So in the first method, you have to actively tell it to check its work every single time. In the second method, it just knows that checking its work is part of being a good agent.
Ideally, yes. And the paper suggests that while in-context is much easier to set up right now, post-training is where we will see the real massive leaps in performance because the reasoning becomes instinctual.
Okay, so we have clearly defined the agent. It's a thinker, it's a planner, it's navigating the fog of the real world. Now, the paper structures this evolution into 3 distinct layers.
The layer cake.
A good layer cake structure. Layer 1 is foundational capabilities. This is basically the toolbox. What can a single agent actually do on its own?
This layer is all about bedrock skills. Before an agent can learn over time or collaborate with others, it needs to be able to function alone. The paper identifies 3 key capabilities here: planning, tool use, and search.
Let's start with planning. We touched on this slightly, but why is planning so hard for a normal LLM? Like, why can't I just tell ChatGPT to plan my vacation?
Well, you can try, but it will likely just give you a generic list. Go to the Louvre, eat a croissant, visit the Eiffel Tower. That is not a plan, that is a wish list.
Right, it's just text generation.
LLMs inherently have very short horizons. They struggle to hold a complex, multi-step goal in their head without getting distracted or just completely losing the plot halfway through.
So how does an agentic system fix this?
Through a process called decomposition. The agent takes that big, vague goal plan, a vacation, and breaks it into actionable subtasks.
Okay.
It says, okay, step 1, I need to book a flight. Step 2, I need to find a hotel. Step 3, I need to check the weather. And then it executes them in a logical order.
The paper mentions a specific method for this called ReWO, reasoning without observation. That sounded super counterintuitive to me. How on earth do you reason without observing?
ReWO is a really clever technique.
Yeah.
It's where the agent completely separates the planning phase from the execution phase.
Oh, I see.
It essentially writes out a blueprint for the entire plan first. It says, I will search for the flight price, then I will calculate the total budget before it actually does any of the searching or calculating.
It's like an architect drawing the blueprints before the construction crew even shows up on site.
Exactly. It completely prevents the AI from getting sidetracked halfway through. If you just start building without a comprehensive plan, you end up with a house that has no doors.
Yeah, you get stuck. And they also mention another method called reflection for planning.
Yes.
Which sounds exactly like what it is reflecting on your actions.
Reflection involves planning with active self-correction. The agent tries to execute a plan, it fails. And then this is the crucial part. It verbally reflects on why it failed and updates the plan.
Wow.
It literally says to itself, I tried to book the flight, but the date format was wrong. So I need to update the date format to day, month, year, and try again.
It is amazing how much that mirrors human problem solving. You fail, you realize why, and you adjust.
Exactly.
And the paper also heavily mentions using code, specifically Python or PDDL, to structure these plans. Why code? Why not just plan it all out in plain English?
Because English is inherently fuzzy. If a plan says go to the place near the thing, that is incredibly hard for software to execute. But code is precise. It is deterministic. If an agent writes a plan in Python, it can execute it and know immediately if it worked or if it failed. It grounds the abstract reasoning in something strict and verifiable.
That makes total sense. If the code throws a syntax error, the plan failed. If it runs cleanly, it worked. It gives the agent crystal clear feedback.
Which leads us perfectly into the second foundational capability tool use.
This is the acting part of the think-act loop?
Yes.
Yes.
This is where we are truly moving beyond just generating text on a screen. Tool use means the agent is clicking buttons, it's calling APIs, it's using a calculator, or it's actually browsing the live web.
The paper describes a three-step process for this: selecting, formatting, and interpreting.
It is a surprisingly complex chain of events. First is selection. The agent has to realize, I cannot answer this user's question with my own internal knowledge.
Yeah.
I need to reach out and use a tool.
Like realizing you don't know the weather, so you need to look at an app.
Right. Then it has to format the request. If it decides to use a weather API, it needs to send the data request in the exact JSON format that specific API expects. That is the orchestration piece.
Which LLMs notoriously struggle with.
They do. And finally, it has to interpret the raw data result that comes back from the tool and turn it into a useful answer.
They mentioned a specific model called Gorilla in this section. Is that a tool using agent?
Yes, Gorilla is a model that was specifically fine-tuned just to use APIs.
Oh, wow.
It was trained on massive data sets of API documentation. So when you ask it to do something, it knows exactly which digital tool to pull from the shelf and exactly how to write the code to use it.
It solves the formatting problem.
It completely addresses the formatting problem because standard LLMs are just historically very bad at getting the exact syntax right for complex APIs.
So Gorilla is basically like the master carpenter who knows instantly exactly which wrench fits the bolt without having to guess.
Exactly. It's specialized.
Okay, so the third foundational capability in Layer 1 is search, but they specifically call it agentic search. How is that any different from me just Googling something? Or even standard RGAV retrieval augmented generation that a lot of companies use right now?
Well, traditional RGAB is entirely static. You ask a question, the system looks up some relevant documents, it feeds those documents into the LLM context window, and you get an answer. It is a one-way street.
Right, does one pass and it's done.
Agentic search, on the other hand, is iterative. It's a loop. The agent looks something up, it reads the result, and then it thinks, wait, this document mentions a new technical term. I don't know.
So it pivots.
It pivots. It generates a completely new search query just to define that new term.
Yeah.
Then it reads that and realizes, okay, now I need to compare this new concept to the original problem. It actively navigates the information space.
The paper talked about something called graph reasoning here too, with an acronym POD plan on graph.
That is a fascinating development in search. Instead of just relying on keyword matching, like finding 10 documents that happen to contain the word revenue, right? Graph reasoning allows the agent to navigate a structured knowledge graph. It can actually see and traverse the connections between entities.
So it understands the relationships.
Yes. It can reason company A owns company B. Therefore, company B's revenue contributes to company A's total valuation. It traverses the logical relationships, not just matching text strings.
That seems absolutely critical for complex research. It is literally connecting the dots.
Literally.
Yeah.
So that completely covers the foundation. Layer 1, a single capable agent that can plan, use tools, and search iteratively. But now we level up to Layer 2, which is where things start to feel, well, a little bit biological, honestly.
Layer 2, self-evolving agents. This is the learning from experience part.
This is the real aha moment of the paper. In Layer 1, the agent is competent, but it is static. If it makes a mistake today, it will make the same mistake tomorrow unless a human developer goes in and fixes the prompt or the code.
But in Layer 2, the agent improves itself.
Yes, without a human ever updating the code.
That is wild.
The paper outlines two main mechanisms that make this possible: feedback loops and agentic memory.
Let's talk about the feedback loops first. This connects back to that reflection idea we mentioned earlier, right?
It does. It starts with self-reflection. This is the agent critiquing its own output before you ever see it. Imagine the agent writes a block of code. Before it hits send or execute, it looks at the code and thinks, wait, that variable isn't defined globally. This script is going to crash. And it fixes it.
That is an internal feedback loop, but there's also environment feedback.
Right. Environment feedback is when the agent actually tries to run the code. It executes the script and gets an error message back from the terminal saying syntax error on line 5.
Okay.
The agent reads that error, which is just a text string. It understands what the error means, and it completely rewrites the code to fix the syntax. It is actively learning from the reality of its environment.
And the paper heavily emphasizes that this is verbal reinforcement learning, which is just such a cool phrase. It means it's improving through words, not just through math or numbers.
Exactly. In traditional AI model training, you use reward scores, which are just numbers. The model gets a +1 for good behavior or a -1 for bad behavior.
Right, it's very rigid.
Here, the reward is an actual sentence saying, you failed because you forgot a comma on line 5. That is infinitely richer information for a language model to process because it explains exactly why the failure happened.
It gives it the context to actually learn.
Yes, which leads right into agentic memory. This section honestly blew my mind a little bit. It is not just talking about the context window, the amount of text the AI can read in one sitting. It's an actual database of lived experience.
Yes. This is absolutely crucial for long-term self-improvement. The paper describes a specific write, read, forget mechanism.
So the agent maintains a database where it actually stores skills or lessons it has learned.
Exactly.
So it essentially has a diary. Like, Dear Diary, today I finally learned how to authenticate with the Twitter API.
It basically does. They strongly distinguish between short-term memory, which is just keeping track of the current task at hand, and long-term memory. How does the long-term work in practice?
If an agent spends an hour figuring out a really clever, optimized way to solve a specific type of database routing problem, it writes that successful strategy into its long-term memory.
Okay.
2 weeks later, if a user gives it a very similar problem, it searches its memory, reads that diary entry, and retrieves that exact strategy.
So it doesn't have to relearn the whole process from scratch. It saves time and compute.
Exactly. And the forget part of write, read, forget is just as important.
Why would an AI ever want to forget something? Isn't more data always better for these models?
Not necessarily. If a strategy stored in memory turns out to be bad, or maybe it becomes outdated because an API completely changed its endpoint, the agent needs to be able to prune that useless information from its memory so it doesn't get confused in the future.
Wow.
It is active gardening of its own knowledge base.
Active gardening, I really like that. It pulls the weeds out so the good strategies can grow. And this whole memory concept leads directly to self-evolving search, right? The agent doesn't just learn facts, it actually learns how to search better.
This is a form of meta-learning. The agent realizes over time, every time I search for the generic word weather, I get cluttered, useless results. But if I search for weather in OAA, forecast API, I get perfect structured data.
So it updates its own internal rules.
It updates its internal policy on how to construct search queries. It literally becomes a better, more efficient researcher over time without human intervention.
That is incredibly powerful. It is building its own best practices from scratch.
It really is. And once you have these incredibly capable, self-evolving agents, you naturally want to start putting them together.
Which brings us to Layer 3, collective multi-agent reasoning. Going from solo to squad. Why use one AI brain when you can use 5?
Or 50. The paper highlights that just like in human organizations or human companies, specialization is the key to complex problem solving.
You don't want one person doing every job.
You don't want one agent trying to do everything either. You want a specialized manager agent, a specialized worker agent, and a specialized critic agent.
The paper calls this role assignment. So how does that breakdown work? The manager does the planning.
Yes, the manager takes the user's prompt and breaks down the high-level goal into pieces. The worker, let's say a coder agent, takes a piece and writes the actual script. Then the critic agent reviews the worker script and aggressively tries to find bugs or logic flaws.
And these agents actually talk to each other.
They do. They pass messages back and forth. And sometimes these roles are incredibly dynamic.
How so?
The overarching system might look at a new user problem and say, okay, this is a complex medical question. I need to dynamically assign a doctor agent and a pharmacist agent to this specific thread. It aligns the agent roles to the specific nature of the problem.
One of the most fascinating parts of this entire section for me was the collaboration structures.
Yeah.
Specifically, the idea of having agents debate each other.
Yes, the debate mechanic is huge.
Right.
It turns out that AI agents, when left to their own devices, can be massive yes men.
They just want to agree.
They tend to agree with each other or agree with the user just to be helpful. This is a known issue called sycophancy.
Right. But that is terrible for actual accuracy. So researchers deliberately structure debates. Agent A is told to propose a solution. Agent B is explicitly instructed to act as an adversary and find flaws in Agent A's solution. And they just argue back and forth.
And this back and forth actually leads to better answers.
Significantly better answers. Through the strict process of argumentation, they naturally filter out hallucinations and logical fallacies. They converge on a grounded truth that neither single agent might have arrived at alone.
That strongly reminds me of the theory of mind concept that the paper dug into. They mentioned frameworks like MindForge and BeliefNet. This part sounded almost unnervingly human.
It is a concept directly borrowed from cognitive psychology. Theory of mind is simply the ability to understand that other entities have beliefs, knowledge, and intentions that are different from your own.
Right, recognizing that you don't know what I know.
Exactly. In multi-agent AI systems, this means Agent A is actively trying to infer what Agent B is currently thinking.
But why does Agent A need to know what Agent B is thinking? They're just software. To collaborate effectively on complex tasks. Let's say I am the manager agent, and I know the worker agent is completely stuck because it misunderstands the goal. I need to be able to realize why it misunderstands so I can clarify my instructions to it.
Oh, I see.
Systems like MindForge are literally trying to give agents this cognitive ability to model their teammates' hidden mental states.
That is just wild. Agents essentially having empathy, or at least a mathematical simulation of empathy for other software agents.
It is absolutely necessary for complex autonomous coordination. Without a theory of mind, they're just shouting text strings past each other in the dark.
Okay, so we have covered the foundation, the evolution, and the team dynamics. Now, for segment 5, let's talk about real-world applications. Because for those listening, this isn't just academic theory anymore. This is happening now.
No, it is being actively deployed in incredibly high-stakes fields right now.
Yeah.
Scientific discovery is a massive one.
The paper mentions a system called the AI Scientist, which honestly sounds like the title of a cheesy sci-fi movie.
It does, but it is a very real, very capable system. This is an end-to-end agentic framework that can autonomously generate novel hypotheses, plan out the necessary experiments, and even write the final research paper.
Wait, it actually writes the academic paper, too.
It drafts the entire manuscript. Imagine a software system that can continuously read the current scientific literature, notice a gap in the existing research, suggest a brand new chemical compound to test that gap, autonomously run a digital simulation to test it, analyze the resulting data, and write up the findings into a formatted paper.
That is mind-blowing. It is automating the entire scientific method itself.
Essentially, yes. They also mentioned another system called Prot Agents, specifically for protein design.
This is for the medical field, right? For discovering new medicines.
Yes. Prot Agents utilizes a planner agent heavily collaborating with a critic agent. The planner suggests a novel protein structure that might theoretically cure a target disease. The critic agent then runs complex physics simulations using external software tools and reports back saying, no, that structure is biologically unstable, it will collapse in reality.
So they debate.
They iterate. The planner learns from the critic's physics feedback and tries again. It massively accelerates the early stages of drug discovery.
Speaking of drugs, there's also Drug Agent.
Drug Agent is another specialized system that coordinates massive knowledge graphs to actively find hidden connections between diseases and potential pharmaceutical compounds.
It's doing that graph reasoning we talked about earlier, traversing the map.
Exactly.
Yeah.
But applied directly to biology and chemistry data.
Moving on to something a bit more digital coding and software engineering. This is where I saw a term in the paper that I just have to ask about. Vibe coding. Is that an actual technical term? What on earth is vibe coding?
I love that term. Yes,
Yeah.
it's a real concept gaining traction, and they put it right in the paper. It refers to a very loose, highly intuitive style of human-AI coding interaction.
Okay.
It means it's becoming less about the human writing perfect line-by-line syntax, and much more about the human just communicating the vibe or the high-level intent of what they want to the agent.
So I just say, hey, make this dashboard look cool and futuristic and make the buttons pop, and the agent just handles all the CSS and JavaScript.
Exactly. You handle the creative vision. The agent handles the tedious implementation details. But for the really heavy lifting in software, they mentioned robust systems like OpenHands.
OpenHands is explicitly described in the paper as a repository-level system. What does that mean practically?
That is the critical distinction. Most current AI coding assistants, like GitHub Copilot, just look at the single text file you currently have open on your screen.
Right, they're very localized.
OpenHands operates completely differently. It looks at and understands the entire code-base repository, which could be thousands of interconnected files. It seamlessly integrates reasoning, planning, and testing.
So it's not just a spell checker for code.
Not at all. It doesn't just write a function. It spins up a test environment, runs the code, sees the specific compiler error, dynamically debugs it, which is called self-debugging, and meticulously verifies that the fix actually works without breaking anything else in the entire project.
That really is the difference between a simple spell checker and a senior co-author working alongside you.
Ideally, yes, that is the exact target they're aiming for.
Then the paper shifts to autonomous web and research. We have systems like GPT Researcher.
GPT Researcher is a perfect real-world example of the structural hierarchy we talked about. It receives a broad research goal from a user. It autonomously creates a comprehensive outline. Then it dynamically recruits specialized sub-agents, little worker bots, to go out and scour the web gathering evidence for specific sections of that outline.
It's exactly like a newspaper editor dispatching reporters to cover different angles of a breaking story.
And then it compiles all their notes back together into a final report. And this directly links to the computer use aspect the paper covers. We are rapidly seeing the rise of GUI agents.
GUI meaning graphical user interface.
Yes. These are agents that can actually control a virtual mouse and keyboard. They can open a standard web browser, physically click on links, type into text boxes, fill out drop-down forms. They navigate the visual web exactly like a human user would, rather than just relying on hidden back-end APIs.
Which honestly makes them infinitely more versatile because not every website has an API.
Exactly.
Which brings us to the final application area, healthcare. And this one honestly feels the most sensitive to me. The system Pathfinder.
Pathfinder is a fascinating use case. It specifically uses multi-agent collaboration to deeply analyze histopathology, which is the microscopic examination of tissue samples.
Okay.
You have different specialized agents looking at different visual aspects of the digital sample or aggressively applying different diagnostic criteria to the same image, and they collaborate and debate to reach a highly accurate consensus diagnosis.
And in oncology, the paper mentions agents are structuring complex decision-making using established medical guidelines.
Right. Human cancer treatment is unbelievably complex with thousands of constantly changing clinical guidelines. These agentic systems exist to help human doctors ensure they are meticulously considering every single relevant protocol and treatment option for a patient's highly specific edge case.
The potential there is just incredible, to never miss a detail. And for those listening, there is obviously always a but with this kind of bleeding edge technology. Segment 6, open challenges. This is clearly not a fully solved problem yet.
Far from it. And to their credit, the authors of the paper are very honest about the massive hurdles still remaining. One of the absolute biggest is long horizon planning.
We talked about planning being solved earlier with things like ReW, but what happens when the plan gets really, really long?
Errors compound exponentially. It is essentially the butterfly effect. If an autonomous agent is trying to execute a complex task that legitimately takes 50 separate steps, and it makes a tiny 1% logical error in step 3. By the time it gets to step 50, that initial error has snowballed completely out of control, and the final result is spectacularly wrong. Current agents still deeply struggle to stay perfectly on track over extended periods of time without human supervision.
It's exactly like playing a giant game of telephone. The original message just gets hopelessly garbled by the end.
Exactly. Another massive challenge the paper highlights is evaluation. How do you actually reliably test an agent?
Standard multiple choice questions aren't enough anymore.
Not for autonomous agents. Knowing the capital of France is fundamentally different from successfully navigating Expedia to book a real flight to Paris. The paper strongly argues we urgently need dynamic environments, complex benchmarks like Wajirina or Science World, where the strict test is to actually accomplish a task, not just regurgitate text.
So we need a driving test, not a written exam.
Yes, perfectly said. We need to see them drive.
And
finally, the biggest, most existential challenge, governance and safety.
This is the critical point for me. If an AI agent truly has agency, if it can act, use tools, spend real money, post on the public internet, who is ultimately responsible when it inevitably breaks something?
The paper highlights the extreme difficulty of auditing these dynamic systems. Think back to the self-evolving agents we discussed. If an agent is constantly learning and independently changing its internal memory and problem-solving strategies over time, the agent you thoroughly tested and deployed on Monday is literally not the exact same agent running autonomously on Friday.
That is terrifying. How do you safety check a constantly moving target?
It is incredibly difficult. It's not static code anymore. It's actively evolving behavior. and that directly leads to the urgent problem of governance of agentic reasoning. We desperately need robust frameworks to mathematically ensure that as these agents independently develop their own reasoning traces and prune their own memories, they absolutely stay aligned with core human values and safety rules.
So bringing this all together for our outro, we have gone on quite a journey today. From foundational capabilities like planning tools and iterative search to Layer 2 self-evolving systems that learn from verbal feedback and actively manage their own memory, to Layer 3 collective teams of specialized agents debating and collaborating with theory of mind.
It is a total, complete reimagining of what an LLM fundamentally is and what it can do.
The ultimate implication, as I see it from reading this survey, is that we are rapidly moving from simply asking the AI a question to giving the AI a job.
That is the exact paradigm shift.
Right.
What if the weather becomes plan and book my entire picnic? How do I write this Python function becomes build, deploy, and test this entire web app? The heavy cognitive load is permanently shifting from the human operator to the autonomous agent.
And here is the final provocative thought I really want to leave everyone listening with today based on this deep dive. We just talked about governance, but really think about this deeply. As these autonomous agents increasingly start creating their own custom digital tools, refining their own private internal memories, and even writing and executing their own code without a human looking over their shoulder every single second, how do we actually technically ensure that their internal invisible reasoning stays perfectly aligned with ours?
It is the ultimate unanswered question of this decade. We are now building software that doesn't just blindly execute written code, but actually independently thinks about how and why to execute it. Are we truly ready for the black box to have its own complex inner monologue?
Something for all of you to definitely mull over this week. Thank you to our expert for joining us on this massive journey into agentic reasoning.
It was an absolute pleasure. Thanks for having me.
We will see you all on the next deep dive.
Goodbye, everyone.